The torque converter has the distinction of being the least understood and probably the most misunderstood component in any piece of construction equipment. Really, this isn't too surprising because it would take a fluid mechanics engineer to understand precisely in every detail just how a converter functions. So our objectives in this program will be limited to three basic areas: how the torque converter works, torque converter terminology used in sales and service manuals, and torque converter advantages and disadvantages. Perhaps the first question we should ask is, why do we need torque converters? To answer this, let's trace the recent history in construction equipment development. Actually, torque converters have been used for many years, but with the development of the POWERSHIFT transmission, they became a necessity. With this new transmission, machines could now be shifted under load, and this led to faster cycle times and less operator fatigue. But the POWERSHIFT transmission created some problems, too. For instance, how could the transmission be made to operate efficiently in a selected gear under varying speed and power requirements? What would keep the engine from stalling in heavy load situations, short of the operator continually shifting to keep the load off the engine? And how could the drivetrain be protected from the tremendous strain produced by instant gear ratio changes? Only the torque converter could solve these problems. Positioned between the engine and transmission, the converter has the unique capacity to sense the torque requirements and automatically increase engine torque, if necessary, to meet load demands. And because the converter acts as a fluid cushion between the engine and the drivetrain, engine stalling is prevented and shock loads on the drivetrain are reduced. In our brief discussion so far, the word torque was mentioned quite a few times. What is torque? Torque is a force which tends to produce rotation. Torque is measured in foot-pounds and is the product of the force applied in pounds and the length of the lever in feet through which the force is acting. As we see here, the lever is the distance between the application of force and the fulcrum being a fixed or stationary point against which the force can push or react. With this crank, a 50-pound force acting through a 1-foot lever yields 50 foot-pounds of torque. However, by doubling the length of the lever, the torque produced is doubled. With this third crank, we can also see that if the lever length remains constant, say at 2 feet, torque could still be increased by increasing the force applied. Keep this point in mind. The more force applied to the stationary fulcrum, the more torque can be developed. Now, with this brief introduction to the torque converter, let's talk about basic operating concepts. Probably the easiest approach to understanding the operation of the torque converter is to first understand the fluid coupling, a device similar to the converter but less complicated. What is a fluid coupling? Basically, a fluid coupling is a device capable of transferring rotary motion from one shaft to a second shaft only by fluid flow, that is, without the aid of a mechanical connection. To illustrate this transfer of rotary motion, we'll use two fans, one running and the other unplugged. The force of air from the running fan will cause the other fan to spin in the same direction. Thus, rotary motion has been transferred from one fan to the other by means of airflow. Of course, the transfer of motion in this example is inefficient because much of the airflow from the running fan does not strike the blades of the second fan. However, if the two fans were enclosed in a housing, more of the airflow would strike the second fan and it would turn more rapidly. The experiment with the two fans illustrates the basic operation of the fluid coupling. Essentially, the fluid coupling consists of two bladed wheels, each with an attached shaft, enclosed in a housing that is completely filled with fluid, usually transmission oil. Notice that there are no mechanical connections between the two wheels. The orange wheel, or impeller, is driven by the engine and acts as a centrifugal pump to pick up fluid in the housing and force it against the blades of the yellow wheel, or turbine. The curvature of the impeller's blades, plus the curvature of the housing, assure that all fluid coming from the impeller will strike the turbine's blades. The impeller then, being driven by the engine, transmits rotary motion to the turbine by means of fluid flow. The turbine is connected to the transmission with a drive shaft and thus transmits rotary motion to the drivetrain. For this transfer of rotary motion from the impeller to the turbine to take place in a fluid coupling, the fluid must flow in two patterns. These patterns, or types of flow, are called rotary and vortex. Rotary flow is illustrated by this simple water wheel. Water flowing from the water box pushes against the blades of the wheel and causes the wheel to rotate. The motion of the rotating wheel carries the water along. Rotary fluid flow, then, is nothing more than the fluid traveling with a bladed wheel. Now, what about vortex flow? Let's look at vortex flow a step at a time. This water wheel has blades which are curved to perform two functions. One function, of course, is to provide a surface for the water to push against to make the wheel rotate. Once the wheel is rotating, centrifugal force throws the water from the wheel. The second function of the blades, then, is to channel the flow of water from the wheel. In this example, the water is channeled off the right side. This side flow is the beginning of vortex flow. And remember that water flowing from the water box has kinetic energy, or we might say has the capacity to do work. The water has already set the orange wheel in motion, but has not yet used all of its energy. Therefore, the water coming off the side of the orange wheel still has enough energy to do more work. We can use this energy by positioning a second wheel with blades curved to absorb the energy of the water and cause the second wheel to rotate in the same direction as the first. Let's take a moment to sum up. Vortex flow is the path the fluid takes when traveling from one bladed wheel to another. And of course, as is evident in this illustration, it is vortex flow that causes the rotary motion of one wheel to be transferred to a second wheel without the aid of a mechanical connection. But the picture isn't complete. We need to know where the vortex flow is going when it leaves the blades of the second wheel. Let's use our simple fluid coupling again to complete the picture. The dotted line arrows represent vortex flow as it actually occurs in the fluid coupling. As the engine begins to spin the impeller, the fluid begins traveling with the impeller, rotary fluid flow, and then centrifugal force ejects the fluid from the impeller. This is the beginning of vortex flow. The curvature of the impeller blades directs the fluid against the turbine blades with great force, rotating the turbine in the same direction as the impeller. Now notice carefully the path of vortex flow. The impeller picks up fluid on its inner diameter, near the center of the housing. Fluid then flows up the impeller blades and exits on the outer diameter or at the top of the blades. Fluid then strikes the turbine blades on their outer diameter and flows through the blades and exits near the center of the turbine wheel. Turbine blades are curved to direct the fluid smoothly back into the impeller to begin another cycle. Can you see what's happening here? The fluid is spiraling from impeller blade to turbine blade and back to another impeller blade in an endless cycle. We've seen that vortex flow causes the turbine to rotate, but when the speed of the turbine is nearly the same as the impeller speed, vortex flow stops. Why? Well, let's assume that the impeller and turbine are rotating at exactly the same speed. We should mention here that this condition cannot exist because of internal slippage in the fluid coupling, but turbine speed can come very close to matching impeller speed. If the speed of both components is the same, both will be completely filled with fluid and both will be exerting an equal centrifugal force which tends to eject the fluid. However, since the forces are equal but opposite, they cancel each other and no fluid can flow between the impeller and turbine. Thus, when turbine speed approximates impeller speed, there is no vortex flow, only rotary flow. What would happen if we imposed a load on the turbine shaft and thus slowed the turbine? In this situation, the turbine exerts less force on its fluid than the impeller, which is driven at engine speed. Since the forces are now unequal, fluid from the impeller begins to flow into the turbine in an attempt to speed up the turbine. Because the turbine is lagging behind the impeller, a small vortex flow is established. If the turbine is completely stopped because of a heavy load, it will, of course, generate no centrifugal force. Since the impeller is still spinning at engine speed, fluid is thrown from the impeller and into the turbine with great force. In this condition, vortex flow is at a maximum. Remember, though, even in this situation, the fluid coupling can transmit no more torque to the drivetrain than the engine can develop. We can see from our discussion of vortex flow that fluid coming from the impeller will strike the turbine blades with increasing impact as the turbine slows down. To illustrate this point, consider the turbine as a truck traveling at different speeds, and consider the fluid coming from the impeller as a car traveling behind the truck at a constant 60 miles an hour. When the truck is going 60 miles an hour, there will be no impact. If the truck slows to 30 miles an hour, there will be an impact, but there will be an even greater impact if the car crashes into the truck when it's stalled. Let's review the important facts we've discussed about the fluid coupling. The fluid coupling transmits the torque or rotary motion of the engine to the drivetrain only by means of fluid flow. There are two types or patterns of fluid flow: rotary and vortex. The impeller is driven by the engine and serves as a pump to direct fluid against the turbine blades to produce turbine rotation. In relation to impeller speed, the slower the turbine rotates, the greater the impact of fluid on its blades. And the fluid coupling serves as a fluid cushion to prevent engine stalling and to reduce shock loads to the drivetrain. All the facts we just reviewed also apply to the torque converter. Let's now see how the torque converter differs from the fluid coupling. In function, the torque converter differs from the fluid coupling in that the converter not only transmits torque, but also increases engine torque if necessary. Construction of a basic torque converter is essentially the same as the fluid coupling, except that the converter has an additional component, the stator. The stator is the reaction member, or fulcrum, enabling the torque converter to increase engine torque. More about this in a moment. This cross-sectional view of a basic torque converter shows the position of the three major components, the impeller, turbine, and stator. Notice that the stator is positioned between the impeller and turbine. One more thing. It might at first glance appear that the impeller is not positioned properly in that it is driven by the engine, but is placed farthest away from the engine. However, notice that the impeller is attached to a separate housing which is driven by the engine. This drive housing actually forms an oil-tight container for the other two working components, the turbine and stator. This assembly is then placed in the main converter housing, which is bolted to the engine flywheel housing. As is evident by looking at the actual components, the design of the blading in the impeller, turbine, and stator is quite complex. The shape, angle, and placement of the blades in these components determine the converter's operating characteristics. Remember when we talked about vortex flow in the fluid coupling, we said that fluid coming from the turbine is directed smoothly back into the impeller. However, because of the shape of the turbine blades in a torque converter, fluid leaving the turbine would oppose impeller rotation if left unchecked. In other words, if flow from the turbine in the torque converter were allowed to take the path of least resistance, it would lug down the impeller. However, turbine flow is not permitted to take the path of least resistance. Here's where the stator becomes important. In order to use the energy of the fluid coming from the turbine, the stator must remain stationary and redirect the flow to enter the impeller in the direction of impeller rotation. At this point, you might ask, why use a stator? The turbine and the fluid coupling gets the fluid back to the impeller with no problem. Yes, that's true. But the stator performs one other very important function as it is redirecting the fluid. It increases the momentum of the fluid. This increase in the momentum of the fluid means that fluid enters the impeller with more force than would the fluid re-entering the impeller in a fluid coupling. In a torque converter, then, the fluid is gaining momentum or force as it is pumped through the impeller, just as in a fluid coupling. However, in the converter, the fluid is also gaining momentum as it is redirected by the stator. The momentum of the fluid coming from the stator is added to the momentum of the fluid resulting from impeller rotation. The combination of these two forces means that the fluid, as it leaves the impeller, will strike the turbine blades with more impact than if the impeller alone were responsible for imparting momentum to the fluid. The torque added to the turbine as a result of the stator's action is called reaction torque. Reaction torque, then, is the key to torque converter operation. It is the addition of reaction torque to the torque resulting from the impeller that allows the converter to develop more torque than the engine alone can deliver. Let's summarize what we're saying here with an example. If a payloader with a full bucket were traveling at full throttle on a good haul road, the torque developed by the engine alone and transmitted through the converter would be sufficient to move the machine efficiently. In this situation, the turbine would be spinning at near impeller speed, and there would be no vortex flow. But if the machine should come to a long, steep grade, speed would begin to decrease even though the engine is kept at full throttle. Because the turbine is connected to the drivetrain, turbine speed would also decrease, and vortex flow would begin. Now, thinking back to our discussion of vortex flow, we know that the slower the turbine rotates, the greater vortex flow becomes. As vortex flow increases, fluid flows through the impeller, turbine, and stator with increasing velocity or momentum. This means that reaction torque will continually increase. Under these conditions, with the load on the machine causing the turbine to slow down, the turbine will be rotating very slowly in comparison with the impeller. But because of the tremendous impact of the fluid on the turbine blades, the turbine will be transmitting tremendous power or torque to the rest of the drivetrain. In fact, because reaction torque is being created, the turbine will actually deliver more torque than the engine alone can develop. In short, engine torque has been increased or multiplied. But notice what has happened. In order for the payloader to develop the torque to climb the grade, speed was greatly reduced, even though the operator kept the machine at full throttle during the climb. This illustrates a fundamental principle for torque converter operation. Speed and torque are inversely proportional. This means a converter will not deliver both high speed and high torque at the same time. If a machine needs more torque than the engine can deliver, the torque converter will automatically supply the additional torque, but will do so at the expense of machine speed. But torque converters do have limitations. It's possible to get a machine in a predicament in which it will not move under its own power, although the engine is turning at a high RPM. What happens in the converter in a situation like this? Since the impeller is spinning at engine speed, but the turbine is completely stopped, vortex flow is at a maximum. Fluid is striking the turbine blades with maximum force, but that force is not sufficient to move the turbine. Under these conditions, the converter is said to be stalled. That is, multiplying torque to its limit, but not able to move the machine. This stall condition takes place at a specific ratio of converter output torque to engine input torque. The ratio is determined by converter design, the shape of the actual fluid circuit, the placement of the working members within the circuit, and the number, shape, area, and angle of the blades in each of the working components. To clear up one point here, remember we said that the torque converter is basically a fluid coupling that could multiply torque. Actually, the torque converter will not function efficiently as a fluid coupling unless the stator is designed to rotate with the impeller and turbine when there is no requirement for additional torque, and these two components approach a 1-to-1 speed ratio. In some converters, the stator remains stationary at all times, and these units are not efficient fluid couplings because the stator causes resistance. In other converters, the stator is designed to be locked in a stationary position by the fluid coming from the turbine during vortex flow, but will freewheel with the turbine and impeller when engine torque is sufficient to operate the machine. Converters with this type of stator will function efficiently during the fluid coupling phase, which is important for the high speed required of trucks and scrapers. In most construction equipment, the torque converter is also doing another job. It is powering the hydraulic pumps. By attaching an accessory drive gear to the impeller and meshing it to two other gears having splined hubs, hydraulic pumps can be driven whenever the engine is running. These pumps are normally used to keep the converter pressurized with fluid and to supply hydraulic oil to the machine hydraulic and steering systems. Now that we've discussed the basics of torque converter operation, let's look at the terminology used in the sales and service manuals. First, the size of the torque converter is determined by the diameter of the impeller. For example, the TD25C is listed as having a 17-inch converter. This means simply that this converter has an impeller 17 inches in diameter. In the basic operations section, we limited our discussion to converters with one turbine. However, some torque converters are equipped with more than one turbine or more than one set of turbine blades. The term stage, coupled with a number, tells us how the converter is constructed in the turbine area. For instance, a single-stage converter has only one turbine. A two-stage converter could have two turbine wheels or two sets of blades in one turbine wheel. The two-stage converter uses the second turbine wheel or a second set of turbine blades to provide more area for the fluid to push against. To explain the term phase, remember that some torque converters can function efficiently only as torque multipliers because the stator remains locked in a stationary position at all times. Other converters are equipped with a stator that remains locked during torque multiplication, but can rotate with the impeller and turbine when the speed of these two components approaches a 1-to-1 speed ratio. A single-phase converter, then, with a locked stator, functions efficiently only as a torque multiplier. A double or two-phase converter, however, can work efficiently both as a torque multiplier and as a fluid coupling because the stator is designed to freewheel during the fluid coupling phase. The term elements refers to the total number of the three basic components: turbines, stators, and impeller. Notice we said stators. Just as a converter can have more than one turbine, so it can also have more than one stator. Multiple stators increase the torque capacity of the converter. Stall ratio is the ratio of output torque to input torque just prior to complete stoppage of the turbine. If a specific converter has a stall ratio of 4.8 to 1, this means that the converter can deliver 4.8 foot-pounds of torque to the drivetrain for every 1 foot-pound of torque supplied to the converter from the engine. As an example of sales manual terminology, the E200 pay scraper is listed as having a two-stage, two-phase, four-element torque converter with a torque ratio at stall of 4.8 to 1. This means that the converter has two turbines, can function as both a torque multiplier and efficient fluid coupling, and has four major components: two turbines, one impeller, and one stator. Also, when this converter is multiplying torque to its capacity, 4.8 foot-pounds of torque are delivered to the drivetrain for every 1 foot-pound of torque supplied to the converter from the engine. One other term that might be encountered is automatic lock-up clutch. This means that the converter is equipped with a device that automatically connects the turbine and impeller when torque multiplication is not required and results in a mechanical direct drive. For example, consider the varying torque and speed requirements of an elevating scraper. When the scraper is in the cut, a great amount of torque is required to keep the machine moving to load the bowl. However, once out of the cut and onto a well-maintained haul road, the torque requirement falls off and speed becomes important. And to get the high speed required, the mechanical lockup engages and provides optimum drivetrain efficiency for faster cycle times. Drivetrain efficiency and faster cycle times are certainly two advantages provided by the torque converter. But advantages don't stop there. For instance, because there is no mechanical shift in the torque converter, a smooth change from one torque-speed ratio to another is automatically provided. The converter, when used with a POWERSHIFT transmission, enables the operator to match load demands with a minimum of shifting. When the transmission is placed in gear and a load applied to the tractor, the torque converter automatically varies its output torque within its designed operating range to meet load demands for the selected gear. This means that the transmission needs to be shifted to another range only when the load causes the converter to operate out of its efficiency range. This all amounts to machine efficiency and less operator fatigue. Other advantages? The torque converter prevents engine stalling regardless of the load. And because the engine can maintain a relatively high RPM under all load conditions, the hydraulic pumps are constantly supplying ample flow to the hydraulic and steering systems for safe operation. The converter serves as a fluid cushion between the engine and the drivetrain. This function, of course, greatly reduces shock loads in the drivetrain and helps to extend component life. But to tell the complete story, we should mention the disadvantage, or at least what seems at first glance to be a disadvantage, of using the torque converter. When the torque converter is multiplying torque, there is a tremendous amount of heat generated. Dissipation of the heat usually entails an additional oil cooler, circulating pump, and related piping. All this adds to the cost of the machine. However, this initial added expense is, in a sense, defrayed by the better performance and ease of operation of converter-equipped machines. We stated at the beginning of the program that we would discuss the basics of torque converter operation. We noted that torque converters in construction equipment will vary in design, and although we did not discuss in detail the operation of the more complex units, remember that the basic operating principles are the same. Remember also that increased product knowledge will help you to gain the respect and confidence of your customers.